In this video, I'd like to talk a little bit about the proof rules for quantifiers. In the first half of the class, we learned about proof rules for the connective. So things like conditional introduction, right, and conditional elimination. Where you go from a conditional and the antecedent of the conditional to the consequent. Now, just like the connectives, quantifiers have their own introduction and elimination rules. So we're going to introduce 4 rules. We're going to introduce universal introduction, universal elimination, existential introduction, and existential elimination. 2 of these rules are very easy, and the other 2 are much harder. Indeed, existential elimination is going to be the hardest rule in our system to apply and even remember. Right, so that's going to be our harder rule. Whereas the easier rules are going to be universal elimination and existential introduction. So I'm going to start from this easier rule. So let's think about what these rules could mean, how could they work. So suppose that you're in a proof. I'll just give you an example to start, and then we'll state the rule in general. You're in a proof, and you've got to a point where you have proven for all x, ax, and bx. And you want to prove b of some specific object O. Well, how would you do that? How would you fill in this gap? The rule of universal elimination allows you to do this by allowing you to do, in the next line here, you can write AO and BO. In general, the rule of universal elimination allows you to go from a universal applying to some formula F to an instance of that formula where you just talk about a specific object O. So if on line M you have a universal formula, then on some later line N, you can just derive F of O. So the idea here is if you know that everybody has the property in formula F, then you know that Bob has the property in formula F. Existential introduction is equally simple, and it goes in the opposite way. It goes from talking about a specific object to saying something general. So existential introduction allows you to go from O has property F to something has property F. Now let's try to see how these rules might be combined to prove an interesting fact. So here's what we're going to prove. We're going to start with the premise that everything is A and B. So maybe the premise is that everything in my domain is both American and a basketball player. And we're going to reach the conclusion that something is a basketball player. Right, clearly this is a valid argument, and it's going to appeal to some of the very principles that I've just introduced. So, as usual, I try to think in terms of my goal before I start any proof. And here I see an existential claim as my goal, and so I'm going to try to apply the same strategy I was using in proofs for connectives. I'm going to try to get my goal by existential introduction. So I'm going to try to get my goal by deriving B of O for some object O, and then introducing the existential by means of the rule of existential introduction. How do I do this? Well, basically the universal elimination rule is going to allow me to eliminate the universal with whatever name I want, because if something is true of everything in the domain, then it's got to be true for every individual object. So here I'm just going to assert AO and BO. And I'm going to say that this follows from universal elimination based on sentence 1. And then in the next step, I'm just going to do a step of conjunction elimination based on step 2. And here in step 4, I'm going to claim victory and say this is existential introduction based on step 3. As usual, go back to the book for the official statements of these rules. Okay, now let's move on and talk about the rule of universal introduction. So here we did a rule of universal elimination. That's this thing here is the rule of universal elimination. How does the rule for universal introduction work? So here's the idea. Suppose that you have a name that we introduce just for the purpose of establishing something. So for instance, you might say this. You might say something like, well, I want to prove that for all x, a of x and b of x entails for all x, a of x. Right? If everybody is American and a basketball player, then everybody is American. I want to be able to prove this. How would you prove this? Well, here's the idea of the universal introduction rule. The idea is you're going to do a universal elimination. And so you're going to get something like AO and BO. And then you're going to derive AO here. And here at this step, you're going to claim universal introduction. You're going to say, well, I've proved this for some object O. And yes, this name O is referring to a specific object. However, I had no special assumptions about this object. In fact, the name O came in the first place from instantiating a universal quantifier. And so I'm going to claim universal introduction based on line 3. Let me tell you the official rule of universal introduction. The official rule tells you that if on some line M you have proven f of O for some name O, then on some later line you can claim for all x f of m, for all x f of x, claiming universal introduction based on line M, as long as there is a big, I don't know how to put it, I'm going to put it in this bluish color, as long as O, the name that you're doing universal introduction on, does not occur in any premise or undischarged assumption. Let's think about what this means. Here are some examples of illegal applications of the rule of universal introduction. So I'm going to say illegal examples. Illegal examples. First, suppose I had a premise in which I claimed AO and BO, and then I did that same reasoning. I said from AO and BO, AO follows from conjunction elimination, and now I do universal introduction for all x, AX, based on 2. This is illegal, and it also proves something invalid, because my premise was that Oswald is American and a basketball player, and my conclusion is that everybody's American. Clearly, everybody's American does not follow from Oswald is American and a basketball player. And the error was that I tried to use a name in my universal introduction that appeared in a premise. Intuitively, what's happening here is the mistake was I assumed something specific about this object. Okay, so let's also see how this could be potentially problematic with undischarged assumptions. So suppose that I had some premise R, but then here I start a subproof for conditional introduction maybe. Right, so here R was a premise, this is an assumption, and now I say, oh, I'm gonna derive AO in the subproof, and then I'm gonna derive for all x, A of x, right? And the same reasoning as before. This is bad reasoning because I am using a constant O in my universal introduction that actually appeared in an assumption. We cannot use constants that appear in assumptions when we do universal introduction, because appearing in assumptions is the same as having something specific assumed about this object. And if something specific has been assumed, then we cannot claim that this object has the right kind of generality to support the introduction of a universal claim. Let's actually see so these two are illegals. So this is bad and this is bad. Let's do one example of an application that is legal but might make you worried that maybe it's not legal. So suppose I want to prove this. I want to prove for all x, if A of x and B of x, then A of x. This is a valid formula. How would I prove it? I'm going to prove it by universal introduction. And so for a specific object, I'm going to assume AO and BO. Sorry, I'm going to derive AO and BO conditional AO. Okay, how do I do that? I assume the antecedent and I derive the consequent. I'll put numbers on this. So this is going to be an assumption. This is going to be conditional elimination based on 1. This is going to be conditional introduction based on 1 to 2. And this is going to be universal introduction based on 3. All right. So this application of universal introduction is legal, even though O was used in an assumption, because that assumption is discharged at the point at which the rule of universal introduction is applied. How do I know that it is discharged? It is discharged because the subproof that contained that assumption has ended, namely it has ended in step 2. To know that the subproof has ended, you just see that the line corresponding to the subproof has been closed off. Okay. These are now the rules that we have of universal introduction, universal elimination, and we also have existential introduction. I'm going to delay in presenting existential elimination until tomorrow in class. And for now, I just want to focus our attention on these 3 rules, and we'll do some practice with these 3 rules during our class meeting.